All right, guys. Let's get in and hack away at a little elementary particle physics here. I've got a picture over here of an interaction. Minus pion is coming up in a bubble chamber, which is full of protons, so it interacts with a proton. So you can see over here in the bubble chamber, here comes the pi minus. Here comes the pi minus, and then there's nothing. But if a neutral particle was produced and decayed into a positive and negative, then that would happen from here to here. And if a neutral particle came off and then decayed to a positive and negative particle, then it would have traveled from here to here. So you can make that assumption, but then you've got to prove that it's true, and you can do that by measuring its energy and momentum and the direction with respect to the original direction that it came off. And lo and behold, that works. Now, measuring the energy of the particles has to do with measuring the density of the bubbles in the bubble chamber. When they first start, and as they go, they start losing energy. So you've got to do it right at the beginning. And here, you have to do it here and here also. And then you're going to have to use momentum and energy conservation to get the total energy for each particle, and then work backwards. So it's just a matter of algebra at this point for this particular collision. Now, if this happened in the plane of of this camera, because when you looked at a picture from the right side, all you saw were a bunch of streaks all in one plane. So you know that these particles didn't dip down or up, but most of the time this particle might be headed down, this particle might be headed up, and these down and up at different directions, and you have to reconstruct a three-dimensional diagram of everything that happened. But for this particular one, that's all that you had to do. Now, to give you an idea of how this was done, when I was an undergraduate, I came in towards the last of the first round of bubble chamber experiments that were being done. And they would project this image onto a 6-foot by 12-foot table. And so that's all that you saw there. So you were in a dark room, and the only light was the light from this bubble chamber event on the table. And they centered it so that you could measure coordinates for where these different events took place. And then you describe generally what happened, and then you would send it off, and they had a reader called a spiral reader, and it would start at the coordinates that you gave, so this coordinate, and read in a spiral pattern to find the exact vertex and the trajectories of these particles as you've recorded them, and including this particle. And then they would take all of that data, put it together, reconstruct the actual paths of the particles in 3D, and from that they would get the momentum and energy of the particles. So this is an interesting one because it produces two neutrals, and in that process, those two neutrals decay into plus and minus particles. And from the rest mass energies that you can reconstruct from their momentum and total energy, you can identify the particles. Now, it's nice when you can see something happening here and going off, but there were a class of particles that this distance right here might be a couple of millimeters, but you could get that distance and turn it into a time from assuming that they were going pretty fast near the speed of light. But what happened if a particle lived such a short amount of time? These are typically 10 to the minus 10, 10 to the minus 16 seconds. And that was fine for getting distances. But what if you had something whose half-life was 10 to the minus 24 seconds? If it was moving at the speed of light, you're not even talking nanometers. It doesn't even move the distance of an atom. So there's no way that you're going to see it in a picture. The question then is, how do you know that something happened? Suppose that these particles were both created right here and you couldn't see it. All you could see is these four particles coming off. Well, it's possible to do that. But let me take an example that's in your book and a little more easily handled. I'll stop right here and I'll go to the whiteboard. So the problem we're going to look at is a proton colliding, being hit by a high-speed electron. And it's going to produce an electron in a very short-lived particle, which itself is going to decay into let's see, proton. I wrote this down wrong. Let me get it out of your book. It decays into a pi plus and a neutron. That's what, you write that clearly. All right, so the first thing, what you see is this. So you've got your electron coming into the bubble chamber, and you have an electron going out, and a pi plus going out, and a neutron, which, if you're lucky, will produce an event, might do something like this. So there will be nothing here. And you see that. So can you tell me what we're looking at here? Oops. Well, this is the path of the neutron, and it comes down and just collides with the proton in a billiard ball collision. And the proton goes off with the energy and momentum that the neutron had. Not an event seen often, but an event that's seen, and you can analyze it. And so at these, and you'll bring them back here, and you'll say they came from the same point, and you measure the speed and energy of the proton, the pi plus, and the E minus, and you can deduce what the neutron energy and momentum was, and they all add together, and energy and momentum are conserved. Where did this particle come in? And the answer is, if you've got two particles coming in, one is stationary, and three going out, they can share the kinetic energy in any way that conserves momentum. Any combination is possible when you've got three particles. But that's not what they saw. They saw that there were only certain ways that this energy was exchanged and the momentum was shared. And so that made people suspect that what happened on a time scale that you can't observe is that the electron came off, but another particle that lasted way too little time to be seen came off. Now when you've got a particular momentum for this particle, you have a particular momentum for this particle. But if you've got three particles, having this electron have a particular momentum in no way tells you what these two particles should have for momentum. They're going to share whatever the momentum is in any way they want to. But if you have two particles coming off, this momentum is much more unique, and the particles that come off from it have a very unique relationship. So it's that uniqueness in the momentum and energy, that the kinetic energy that these two particles shared, that convinced people that it was this kind of decay and not just a straight three-particle decay like this. These particles, because you can't observe their track, are called resonance particles. And some of them can be very massive, much more massive than the proton. And in fact, that was the discovery, this reaction of the electrons hitting a proton, that was the discovery of the delta particle, the delta plus. And those other particles that you see have very short half-lives. So what was taking place in here was the invariance of this relativistically. That does not change from one reference frame to another. And you mind reminding me what that's equal to? I'm sorry, I've got to. So this is an invariant. It means no matter what frame of reference you look in, this has the same value for the object you're looking at. What is that invariance called? It's given a name.
Rest mass energy?
Yes, rest mass energy. Now, you'll hear people talk about and say that the mass of a particle, didn't write that in the right spot, is gamma mc squared. And that's really not a good way to think about rest mass, although it makes some calculations easier and it will always work. It's this idea that's the big idea. The rest mass energy is the invariant. So if you look at all the masses that you can extract from these events, the interesting thing is here are the number of events, and here's that invariant mc squared. And what you find in this reaction is this happens at the 12, I want to think it's 1213, I may be off a little bit. It may be 1230. You get that, and you actually get some others out here. And these are also referred to as resonance particles. And so when you do this collision, all these collisions, and you analyze all these and go back to figure out what that energy, rest mass energy was, assuming two particles coming off, you get the fact that there may be multiple particles, almost like the particle that's created with this mass has excited state energies. Now, if that particle is a unique particle, how can it have an excited state energy? How can a particle all by itself have an excited state unless it has structure? And that structure is what led us to the idea of quarks. So if we go back here, this is where we're headed. Atoms have structure, nucleus and the electrons around it. A nucleus has structure, neutrons and protons. A proton or a neutron has structure. Those are the quarks. We hope this is the end of it. Right now, we've never seen structure in the electron down to this dimension, 10 to the minus 18 meters. Same thing with the quark. It's probably on this dimension. And so it ends up that because the proton and neutron, which are baryons, have these quark structure, we surmise that all the others did also. And the theory came out that the baryons are, and the hadrons, which are baryons and mesons, are all composed of three quarks. And I'm sorry, the mesons are composed of two quarks, and the baryons are composed of three quarks. What about four? What about one? Well, one doesn't work for us. And the reason is that the properties of the quarks are so unusual. So let's take a look at, let's see, the properties of some of the quarks. Where are they? Here they are. They all have spin 1/2, so they're Fermi-Dirac particles. And what do we know about Fermi-Dirac particles? How many can have the same number of energies?
Just one?
One.
Right. You can only have one particle in any given energy with any given set of quantum numbers.
Let's go.
Yes, sir.
Look at their chart. They're either 1/3 of the electron charge or 2/3 of the electron charge. Only once in physics history has somebody seen 1/3 or 2/3 charge, and that was Millikan. But he crossed it out in his lab notebook because he felt like they had lost sight of the one oil drop they were watching and had actually picked up another one. Before he measured the charge on it, he had canceled it out. His graduate student went ahead and calculated the charge, and it came out to be 1/3 E. But he had
no one's been able to do that since.
No one's seen anything like that since, except for one other fellow from Stanford who was using superconducting balls in a new version of the Millikan oil drop experiment. And he claimed that he found a fractional charge. But somebody in his lab had taken the tiny sphere with that charge on it and had put it back into the container with all the other spheres. And he wasn't going to go back and try to find it. So he measured one to have a fractional charge. Don't know if either one of those is real or not. But he would have this fellow from Stanford, it was his thesis that he was doing this on. He would have had to measure several thousand more spheres to try to find that one again, and it wasn't worth it. So in reality, we've never observed a fractional charge. So therefore, you can never have a particle that's one quark. You can have particles that are two quarks. You can put together a plus 2/3 and a plus 1/3. You can put together a minus 2/3 and a minus 1/3 charge to make a meson with two. If you've got three particles, you can have two 2/3 and one 1/3 in various combinations, or all 1/3 charge. Or for that matter, you can have all 2/3 charges. You just have to have the pluses and minuses right. So there are many more possibilities for particles with three quarks. Are there four quark particles? We don't know. There was a little bit of evidence for a 5 quark particle, but nobody really believed it. And they never truly published it as the discovery of a 5 quarks. So I guess there were reasons for not believing that experiment. Baryon numbers are all either plus 1/3 or for the anti-quarks minus 1/3. Some of them have strangeness quantum numbers. Some have something called charm, which...
How do they have charm? They don't have personalities.
Well, if you are strange, you have charm. Some have bottomness and some have topness. Now, I will say that they have fun with these names. One group out of, I don't remember if it was Harvard or one of the Ivy League, had done an experiment, and they proved that they had observed a particle that had only one bottom quark. And so they titled their paper Observation of Bare Bottom Particles. That's a physics joke, guys.
I laughed. You heard me.
Right. Okay, so let's see what happens when we put these things together. I'm looking for my picture here. Here it is. Okay. If you've got your textbook, you can go to the page with table 15.3 and look at it. But I don't have any way to show you both these. Well, I guess I can do this. Let me copy it. I'll just paste it in here. All right, so we can look at it here for a minute. We've got a meson with an up and an anti-down quark. So what's its spin?
One.
It could be one, couldn't it? What do we do with spins when we put them together?
Add them.
Add them. Yeah, and we add them in funny ways, don't we? So it could be spin 1 or it could be spin 0. What's its charge going to be?
0.
Up quark is plus 2/3 E. Anti-down is plus 1/3 E. So that'll be plus 1 electron charge. Baryon number. So it'll be plus 1/3 and minus 1/3.
0.
See this, right?
Yes.
See the table? Okay.
Yeah, we
So
can.
it has no baryon number, so it's not a baryon. And then the ups and the downs don't have strangeness or charm or bottomness or topness. So we don't have to worry about that. How about a proton? Okay, so a proton apparently is 2 up quarks and 1 down quark.
That be spin 3 halves.
So we've got 3 spin 1 halves, right? So you add the first 2 together, you get a 0 or a 1, and then you add the 1 half to that. So you have a 3 halves, 1 half, 1 half, 0. What's the proton? It's a spin 1 half.
1 half. Yeah.
Okay. What about the baryon number? What is that?
1/3.
Each one of these brings in 1/3, so you add them together and you get 1. And that's, if you go back to the table, I'll flip over here. Proton has a baryon number of plus 1.
So it doesn't matter if those are minuses?
They are, but the up and down quark are here. And they're both 1/3.
Oh, I was looking at anti-down.
Yeah. So how would we make an antiproton?
2 ups, or 2 anti-ups and 1 anti-down.
2 anti-ups and 1 anti-down. That would give us -1 for the baryon number, which is what it's supposed to have. Could we have some combination of up and anti-up and down? Would that work? That wouldn't
Probably wouldn't be a proton then.
it wouldn't be a baryon, would it?
Yeah.
So you're going to have all three particles or all three anti-particles. So what's a neutron?
One up and two downs.
Yeah, one up and two down. And so the charge one up is 2/3 and the two downs are minus 1/3. That gives us a zero charge, doesn't it? And the baryon number, it comes out to be +1. So what would the anti-neutron look like?
An anti-up and two anti-downs.
Yeah. And that gives us the -1 baryon number, and it still gives us a neutral charge. So that's how the game's played. And here I've got a K minus. And so what's the baryon number for a K minus? If you construct it from this stuff. A strange quark and an anti-up.
Would it be zero?
No.
Wait.
So
Wait, you asked what the baryon number would be? Oh,
so the anti-up
also get a charge.
Zero, baby.
So it's not a baryon, is it?
No, sir.
So that makes it a meson. All right. What's its charge? Let's see. The anti-up is minus 2/3 E. What's the strangeness quark?
Minus 1/3.
Minus 1/3. So that gives us -1. So it's that's the K minus. And if we go look at the K minus, it's an antiparticle, isn't it, of the K plus. So what's the K plus made of?
An up and anti-strange.
An up and an anti-strange. So the up would have plus 2/3 charge, and the anti-strange would have plus 1/3, so it'd be positive. +1. Baryon number is 0. So the antiparticle involves making all the quarks the anti of whatever they were. Here's where a problem came in. What if I have 3 d quarks? Is that possible?
Yeah.
No.
Yes, it is.
What will be the charge of a particle of 3 d quarks?
Negative.
-1.
Yeah.
-1. What would be the baryon number?
1.
1. And strangeness and all that other stuff are all 0. All the d quarks have the same quantum numbers. That violates the Pauli exclusion principle for spin 1/2 particles. That means there's a quantum number missing. That quantum number is color. And instead of having 2 values, it has 3 possible values. So instead of assigning numbers to them, we used red, green, and blue. And it's that addition that required, first of all, you can just say that, and you're very smug, and somebody's going to ask, how does that fit into the Schrodinger's equation for this? And this required creating a whole new idea of quantum mechanics called quantum chromodynamics.
Now you're just making things up, Dr. P.
That sounds like it, doesn't it? And they made it similar to the relativistic Dirac equation that had worked so well with a few corrections for quantum electrodynamics. And so they just said, we'll create something in parallel with it, and it works. And it's that idea that's called the Standard Model. So, with that in mind, that means you can, before you have to pay attention to red, green, and blue, you can create a particle with 3 down quarks or a particle with 3 up quarks. What's a particle with 3 up quarks going to be?
Don't know.
A squared proton.
So what's its charge?
Its charge is 2e.
Is 2e. Okay, so let's go down here and look. Is there anything down here with the charge of +2? Do they have the charge on here?
Doesn't look like.
There it is. Right there.
Delta?
Delta 2 plus.
Mm.
Baryon number of 1. No strangeness. Three downs have no strangeness. We got, let's see, was it 3 downs? We used 3 ups, 3 ups. So with the 3 ups, we get plus 2 for the particle. It looks like that's the delta plus plus resonance particle. We can do the same thing with the 3 down quarks. Yeah, but that gives us something that just has a -1 charge. And so the question is, can we identify which chargers are which? Can we figure out from the properties we've got listed here how to make these baryons and these mesons from those quarks? Excuse me. So here's part of the hint. When particles interact, they can change not only the color but the makeup of the quarks. Let me see if I've got that. Yeah, I think I erased it. Oh, here it is. So here's the thing we need to think about right here. This is a pi plus, which remind me was made up of 2 quarks, quark and 1 anti-quark. Why do you have to always have them made of 1 quark and 1 anti-quark? go back to this. Why are mesons always one quark and one antiquark?
So the baryon number is 0.
That's it. So the baryon number is 0.
So what's that W plus? What's that mean?
That's an exchange particle. And we're going to go back next time and talk about the idea of exchange particles and then how they work to turn one particle into another particle. We'll start with this vision right here of a neutron and a proton interacting with each other to turn each other into a different particle, a proton to a neutron and a neutron to a proton. So next time what we're going to do is to talk about Feynman diagrams, how to make them, and how these exchange particles come into being and what they mean. So that's all for today, right on time.
Dr. P, is Monday our last class?
No, Wednesday is.
Okay, cool. I guess we get our quantum mechanics degree then.
You get your quantum experience degree. Quantum experiential. Yeah.
Hey, Dr. P, so once the seniors graduate, does that make us officially physicists?
Of course it does.
Of course, wink, wink.
So we can say with certainty that we have no idea.
No, you can't. You're bound by Heisenberg there. You probably can't tell us. But sometimes you get lucky. Isn't that the Heisenberg uncertainty principle?
Sounds about right.
All right. Any questions?
That is all. Thank you.
All right. I'll
Thank
have the tests, email them to you tomorrow, and you can work on the corrections and have those in on Wednesday.
And the papers due on the day of the final?
Well, actually, let's say your papers are due the last day of finals.
Okay.
Cool, thanks.
That's like May 6th.
We had to be flexible with our rules, so I'm going to be flexible with theirs.
Let's go, Dr. B.
I love it.
That's what I'm talking about.
All right. Is that when you want our portfolios too, the last day of finals?
Yeah.
Okay.
Do we have like a rubric for those, or like a?
Yes, I sent you one. Do a search in your email attachments for Frank Odom, ODOM.
Yeah.
Yeah, I think you also attached like for just the seniors. You attached like a drop in the Dropbox. There was one for just seniors that has the portfolio and stuff in there.
Oh, there is?
I think so.
Yeah, I think there is.
Oh, okay. Well, good.
Do we have rubric for the paper or?
No, it's just a paper.
Write enough about the stuff in there and then turn it in.
That's like, you want like introduction, abstract, stuff like this, or just an essay paper?
Well, you should have diagrams and I mentioned that you should have an appendix with some textbook problems that are relevant to what you're talking about, and you can discuss those in your paper.
All right. So you want us to solve some related problems in our paper?
There should be some textbook problems related to what you're doing.
All right.
It'll be all right.
What are you doing? Alaa, what are you doing?
I'm doing Raman spectroscopy. So
Okay, so there won't be in this book. I'll send you some.
all right, thank you so much.
Yeah. If anybody else needs some problems that they don't find in the book, I can send you some that you
Do
can-
we have our topics?
Do I
Yeah,
have your
we-
topics?
We,
You have
we
your
picked those a
topics.
while ago.
Okay. Mine's just a page turner, Dr. P.
Yeah, I'll bet. What is it?
I don't know if you can tell me. If is there some place where our topics are written down?
Yeah, the email you should have sent him a while ago.
Yes. Yeah. So this is a confession here, huh?
I
Have a topic? Do you need a topic, huh?
David's been busy. Cut him some slack.
yeah, I'll take a topic.
You want an elementary particle, nuclear, solid state?
Let me get back to you.
Awfully quiet there.
Let me go dig into the textbook, and I'll
Find something that's interesting to you.
okay, can do.
All right.
Thank
Great.
you.
All right. See you guys later.
All right, Dr. B, thank you.
All right,
Yeah.
Thank you.
Thank you.